And then on Wednesday, the first hour of Wednesday, usually I can do it in about 45 minutes. We're going to go through the 4 possible ways that this model can work. And then you're going to have your next homework assignment. And the next homework assignment will take a little brain power. It will not take calculators. One thing you'll need to keep in mind is no matter how I ask the question, there's only 4 possible answers. It's going to be one of those 4. And hopefully that'll make more sense as we go through it. But it's easy once you get the hang of it, but kind of hard to get over that hump. So make sure you're here on Wednesday and to get all that done. All right, so at the end of class last Wednesday, we were talking about interspecific competition. And so I found that I was looking for something specific, comparing the types of intraspecific competition to interspecific competition, which is what our next topic is before we start modeling. And I couldn't find anything that I liked, but I did find this, and I liked it. And what this is a comparison between intraspecific competition, which we've already talked about. You all remember the 2 types of intraspecific competition? One was scramble, and the other was... I don't know, for some reason I went blank. Yeah, contest. I want to make sure I didn't get them backwards because I was reading the other 2 before class real quick. Yeah, scramble and contest. So intraspecific competition, the first part there, hopefully we've got that part down. Intraspecific competition is same species. Interspecific competition is we're now doing different species. That's a big topic for today. We're going to look at different species and how they impact each other's population growth. The second one we might not have thought about quite so much. Intraspecific, because they are the same species, they're competing for all the same resources. But in interspecific competition, because they're different species, they have different environmental needs, and so they're only going to be competing for a limited amount of resources, depending on what it happens to be. So a lot of times in these examples, it's food, right? But they're 2 different species, so their other environmental needs are different. So I believe when we talked about niches, we talked about the competitive exclusion principle, and we said that no 2 species can have exactly the same niche. That's basically what this is saying. They're different species. In order for them to coexist, they can't have exactly the same niche. They just have a little niche overlap, and in that overlap, they're competing for some resource. Okay, so they're not competing for everything. The competing individuals have similar adaptations when you're talking about intraspecific competition because they are the same species. In interspecific, they have different adaptations. So last time we looked at deer and turkey. Those are different species. They have different adaptations. They just happen to both eat acorns. Oh, I had a great time this weekend. I was upstairs in my house, and I've got these big picture windows, kind of triangular windows. And the turkeys were just down at the base of my driveway, kicking in the leaves all day long. After, I think, hickory and acorns down there. Hickory nuts and acorns. So it was kind of fun. But that's different. I didn't even see the deer. They didn't seem to... I have seen them up there doing the same thing. I did not see them at the same time this weekend. All right, so they have different adaptations. And intraspecific competition can be more severe because they do have all the same needs. And interspecific, it kind of depends, I think, a little bit more than this is suggesting. So that's just a little roundup to compare the 2. We're, of course, today are interested in interspecific competition. And specifically, we've already defined it, and so now we're just going to talk about the 2 types. And so we had 2 types of intraspecific, scramble and contest. Now we have 2 types of interspecific, which is going to be exploitative and interference. Exploitative and interference. And so what I was looking for was a table that compared those, and I couldn't find one, sorry. Exploitative is the use of one use of the resource reduces it for the other one. And so that's very much the turkey deer example we discussed on Wednesday. And so the outcome is determined on how efficiently the species use that resource. And so if one of them is more efficient at collecting and using the resource than the other, then they're going to be able to outcompete the other. Except that this particular one is more like scramble competition, in that the use of the resource by one species reduces what's available for the other, and vice versa. And so the overall effect, so that we're thinking about what our main topic today is, which are modeling population growth, is that if both of them are using the same resource, making it less available to the other, overall the carrying capacity is going to come down, right? Overall, the environment is going to support fewer of both of those species because they're sharing that resource. So they're going to have an impact on the population growth of the opposite species. Is that making sense so far? And so that's when I moved my two pictures here. So these are my two photos of the deer and the turkeys out, and the elk and the turkeys out feeding. The main thing here as we finish up exploitative competition is that they are not physically interfering with each other. It's just they're using the same resource. Like I said last time, I'm not going to say that none of you have ever seen a deer kick a turkey. I haven't, and I sit there when I see this, and I'm always fascinating. I sit there and watch it, and they just all seem to rustle around eating their acorns. But the acorns that the turkeys eat are not available to the deer, and vice versa. Okay, so that's exploitative competition. The second type of interspecific competition is interference competition. Let's get it all up there. And in interference competition, this is where you do directly interact with each other. And so one of them is going to try to take the resource from the other, essentially. And so in this case, in terms of comparing it to intraspecific, this is more like contest competition, where you have a clear winner and a clear loser. And so one species generally is going to win the interaction, and the other species is going to lose. However, as we talked about interspecific competition last time, it's still minus for everybody, because the loser does have to, the winner has to expend energy defending its resource from the loser. And usually it's not always as clear cut. And so I pulled up some pictures right before I came to class of some lions and hyenas. So we can talk about lions and hyenas. All right. And so I brought some conflicting photographs on purpose. So at the top you see the lion on the carcass with the hyenas. At the bottom you see the hyenas on the carcass and the lion walking away. At the top you see the hyenas chasing the lion, and at the bottom you see the lion chasing the hyena. Right? And I did that on purpose because it's not always as clean as a textbook's going to say. Generally speaking, in this particular interaction, most of the time the lion is going to win. It's the winner. And even in this bottom picture where the lion is walking away from the carcass, that lion is probably finished eating. It's either finished eating or the hyenas finally amassed enough individuals to run it off. Okay. But it is good examples of both of them, regardless of who wins and who loses, had to expend energy in the interaction. All right, any questions about exploitative competition and interference competition?
Would you say, like, exploitative competition can also be, like, I know they might not interact every time, but like starlings and woodpeckers, or house sparrows and bluebirds, like using the same nesting like spaces? Because I know that the
starlings would be a poor example. They would be interference. They do physically interact.
Right.
It would be rare for them to take a active cavity without physically interacting.
Right. Or I think, did I say, I meant interference competition, not exploitive.
Yeah, that would be interference, right?
Right.
Yeah, it would be interference.
Okay.
Because they're very aggressive. Now on the woodpeckers, they're just like, here's my cavity, which is kind of lame on their part. But they also haven't, starlings are new to the interaction. They haven't really evolved good defenses against it, even though they have a good one attached to their face. But they also have the ability to go build a new cavity, but that's energy that they have to expend from that interaction. Okay. Exploitative and interference. Anything else? Okay. Hey, this should be familiar. This is our logistic growth formula, where we have an instantaneous change in population size over an instantaneous change in time. And that equals our instantaneous per capita growth rate times the population size. And then this one is corrected for intra-specific competition, where you have our carrying capacity minus the population size divided by the carrying capacity. And so just to continue our review, the first part of the equation represents the exponential growth formula, which is the potential for the population to grow without any type of interactions, to grow with unlimited resources, no interference whatsoever. And then to get a logistic growth formula, we then are going to add intraspecific interactions, so interspecific competition. That's going to keep the population from being able to grow exponentially and causes the population to settle in at what we call the carrying capacity, which is the number of individuals the environment can support. And this was one of the questions on exam 2, was to, I think I had a circle of one part and square the other, but basically to find these two pieces of the equation. And I did that on purpose, knowing what we were going to do now. All right, any questions or anything we need to review here? Okay, so the formula that we just had was for a single species. That's all we've done so far. We've just looked at a single species. Now what we want to do is to look and see how species interact with each other. So in other words, we need to make a formula for every species involved in the interaction. That means that we need a formula that's going to describe population growth for species 1, and a formula that's going to model population growth for species 2, and a model for species 3, and a model for species 4. However many species we want to put in there, we need to have a model for their population growth. Lucky for us, we won't ever go past 2. But I do need you to understand that we could be doing this for multiple species. In reality, that's usually not just 2 species involved, right? I gave you the lions and the hyenas. We could add in there the vultures, for example, that are usually hanging around in the background as well, and other species, other scavenger species that harass the lions. All right, this isn't that hard. For species 1, we'll just add 1s to everything, okay? Everything that's specific to species 1, I should say. And so now we have N1, which is the population size of species 1, R1, which is the growth rate for species 1, K1, which is the carrying capacity for species 1. Piece of cake. What should we do for species 2? Add 2s. Yeah, so for species 2, we'll just say N2, the population size of species 2. R2 is the growth rate for species 2, and K2 the carrying capacity for species 2. That was easy. So far, so good. It's a good start. However, these two formulas do not interact with each other, right? It just has species 1 growing logistically and species 2 going logistically. The only thing that is stopping their population from growing exponentially in both of these models is intra-specific competition. But we're more interested in this PowerPoint about interspecific competition, right? And so the formulas on the previous slide only account for intraspecific competition, so we need to add something to our formulas that's going to account for interspecific competition. Still okay? All right. And so for species 1, what we're going to do is add alpha N2. All right, alpha N2. So N2 we've got. That's the population size of species 2. Right? The alpha is the new part here. So read what alpha is carefully. It is the competitive impact of species 2 on species 1. The competitive impact of species 2 on species 1. We are going to be doing this as an intellectual exercise, so we're never really going to put a number to alpha, other than to say if alpha is 0, in other words, there's no competitive impact between the two species, then the population will continue to grow logistically. But of course, we're interested in competition, and so there's going to be some amount of competition between the two species, and that's going to impact the growth rate, not the growth rate, the population size that N1 is going to be able to attain. So what should we do for species 2? Yeah, it's going to be beta, but you're on the right track. We're just going to give it a different, we have to give it a different letter because it's the opposite, right? But you're absolutely on the right track. And so we're going to add beta N1. And so N1 being the population size of species 1, and beta being the competitive impact of species 1 on species 2. And competitive impact of species 1 on species 2. And again, if that's 0, then the population growth for species 2 will just be logistic growth. That's the way these models are going to work. All right. Any questions before we put these into the models? All right. And so as we get into competition models, well, I guess we're kind of already into them. But as we're doing competition models, and then next week as we get into predator-prey models, what we're going to see is we're going to run those models, and the outcome is going to be decided by these two models being run at the same time. All right. And so in this case, we've got two competitive species, N1 and N2. And then next week, we're going to have two species again of predator and prey, which means we'll need how many models? At least one for one predator and at least one for one prey. And then if we wanted to have lots of prey, we would have to have a model for every prey species. If we wanted to have more than one predator, we need a predator model for every predator species. Okay? Just like in this model, we need to have a formula for every competitor in this interaction. We're staying with 2, but we could add in species 3, species 4, species 5, and we would need a formula for every single one of them. Okay? That was looking ahead a little bit. So for species 1, the formula becomes very similar to what we saw before. And so this part right here, oh, too short. Could also crack people's knuckles now, right? All right. So this part right here, still exponential growth. This part right here is still logistic growth. And then we're adding interspecific competition right here. Okay? So just like before, I would expect you to know the different parts of the equation and what they represent. So exponential growth, intra-specific competition, interspecific competition. Okay. As we're looking at this equation, alpha is the competitive impact of species 2 on species 1. And just like I said before, if it's actually 0, if they are not competing, then that becomes 0, and this whole thing becomes 0, and therefore it's just going to grow logistically. And so this really is only going to alter the population growth equation if they are actually competing. Any questions about that? All right. Then the second equation shouldn't be a big surprise. It's the same thing, except now we're doing species 2. And so it's the population growth of species 2 and how it might be impacted by a competitive impact of species 1. Okay. The last part of this is just what I was trying to get you to think about before. If beta is 0, this whole thing becomes 0, and the population will just grow logistically. This is also saying is if they are competitors, if N1 and N2 are competitors, but there aren't any individuals of N1 in the area, and so N1 is 0, that has the same effect, right? So 0 times their competitive impact is still going to be 0, and the population will grow logistically. Okay. So there's 2 ways to cause it to grow logistically. Either they don't compete, or there are no individuals of the other species present. All right, looks like next I just put the boxes and do what I just said. So there's your box for exponential growth. There's your box for intra-specific competition. And then finally, there's our new box showing inter-specific competition. All right. We're actually almost done with the introductory part. Not too bad. Any questions about this so far? Okay, trying to take our time anyway. All right. In this model, the carrying capacity of species 1 is controlled by two things. Two things are going to determine the carrying capacity. One is the population size of species 1. In other words, intra-specific competition. Right. That's the same as just your regular logistic growth model. Intra-specific competition determines how many individuals the environment will support. But now we have a second thing that's going to impact their carrying capacity, and that's the competitive impact of species 2. Oops, let's get up there. Competitive impact of species 2. Let's get it all up there so that I can see it. There we go. And so if we go back and we think about our example of the deer and the turkeys both eating acorns, if you remove all the turkeys, then the only thing that's going to impact the population growth of the deer are going to be competition for the acorns with each other, and the population's carrying capacity is going to be whatever, let's say here. Now if we put the turkeys back in, the deer and the turkeys are both eating acorns, meaning that there's less acorns available for the deer. And so what that's going to do is it's going to cause the carrying capacity to be here. It's going to lower the carrying capacity of deer because there's less food available, because it's being eaten by the turkeys. Okay, has everybody got that? That's what this is trying to tell you. And so without competition, carrying capacity is set by intra-specific competition. With competition from other species, then it's going to be lower, and it's set by both intra and inter-specific competition. It's set by both. All right, brought my markers. Let's go with black. That tends to be easier to erase. Before I get, so we've kind of done to this bullet. We need to address the second part of this slide. So what we're going to do next week, it is just Monday, right? What we're going to do on Wednesday is we're going to build models. And we're going to build models that are just graphs. That's pretty common. You've probably built some models that were graphs before, like if you've encountered island biogeography, that's a model that we generally don't actually do the mathematical calculations, we just look at it graphically. So that's what we're going to do. And on these models, we're going to put the population size of N1 along one axis, and we're going to put the population size of N2 along the other axis. And then we're going to look to see what happens to the population growth of both of these species. All right. So far, when we did our logistic growth model, we didn't have N2 over here. There was no N2 yet. We just had time, right? And we said that population size would reach a particular size, and that was the carrying capacity. And so the same thing's going to happen here. This is going to be the population size of N1. So if it's increasing, this is more individuals. Decreasing, this would be fewer individuals. Right? So N1's moving along this axis. And so somewhere along this axis is going to represent the carrying capacity of species 1. Whatever number that happens to be. Along this axis, we are only looking at species 2. Okay? Species 2. And it's going to be doing the same type of thing. If we go this way, then this population is going down until it would approach 0. And if it's going this way, the population would be increasing. And so somewhere along this axis is a number that represents the carrying capacity of species 2. Okay, so we can put it anywhere. Let's put it here for now. Okay? So this is the population size that the environment will support for species 2. This is the population size that the environment will support for species 1. Now, so far in the models, while we were building them a second ago, what I got you to think about is if there are no N2 around, or if N2 doesn't affect N1, there's no competition between them, then N1 is just going to react normally, have normal logistic growth, reach its regular K1. Right? Everybody seemed to be okay with that. Now what's happening though is we're going to say there is competition. And if there is competition, then N1 and N2 are going to lower how many individuals of each species can be present in the environment. And eventually, one species can outcompete the other. That's one option, right? And so that's kind of what the last part of this is about. So it says the population density of species 2 that will exactly equal the carrying capacity of species 1 is K1 over alpha, right? That's actually along this axis. It's saying how many individuals of species 2 do you need to completely outcompete species 1? And that number, whatever it is K1 over alpha. So it's physical. It's on here somewhere. So let's say it's here. Okay. That means that if N2 can reach this population size, N1 cannot grow. It will be here at 0. In other words, we have the two models running together now. All right. Now, keeping that in mind, what's the population size of N1 that will completely suppress N2? Oops, there it is. Yep, K2 over beta. Well, let's say it's over here. And so if N1 reaches this population size, then it will completely suppress N2. N2 will be 0. Now I put these two things on the mark on our board here for a specific reason, in the specific places for a specific reason. And so in this case, K1 over alpha is less than the carrying capacity that this species can get to. Okay? For some reason I smudged it. And so is it realistic to think that this species can reach this number considering the carrying capacity for this species is up here? Yes. Now let's look at this situation. This is the carrying capacity for species 1. This is what the environment will support of species 1. Is it realistic that they'll reach this number? No. And so without doing all the fancy lines and arrows that we're going to learn how to do on Wednesday, so without doing that, what's going to happen in this situation? Or what could potentially happen in this situation? This one is able to reach a population growth that suppresses and gets rid of N1, but N1 can't do that.
So then N1 will be outcompeted.
There's a real potential that N1 will be outcompeted. Okay? The potential is there. Depends on other factors, of course, but it's there. Will N2 ever be outcompeted in the way that I set up our axes today? No, never in this situation. okay? And won't go too much further into that today. But that is the type of thing that we're going to be considering on Wednesday. Okay, got one more slide we go through today. Okay, and so if you understood everything we've done to this point, we should be in good shape for Wednesday when we start to do the actual models themselves. Okay. Any questions before we look at what the possible outcomes of this type of interaction is going to be? Okay, I told you we had to use our brains. I had to use mine a lot too, but I think we're okay. I think my brain didn't glitch too badly. All right, so as we do this, I told you, even on your homework, I'm going to give you lots of different ways to work with these models so that you think about them and hopefully really get the 4 models down. But for every question I ask you, there's only one of 4 possibilities. That's it. At the beginning of class on Wednesday, that's what we're going to do. We're going to draw out all 4 options. And then your homework, the first part of your homework is draw all 4 options. I'll just tell you that straight up. And then I'll start giving you situations. You know, this species outcompetes this one every time and stuff like that. And you have to think about which of these 4 models is appropriate. All right? All right, so the first one is that species 1 wins. That's not what I set up over here. But how might I modify what I've done so far to allow species 1 to win? I'll just flip, I need to flip both of them, right? But I'll flip both of those, right? And that would allow species 1 to win. If I do that, and species 1 is able to drive species 2 away, then we get a stable equilibrium, meaning that you do have a clear winner in that interaction. And then I have it drawn on the board as if species 2 is winning. And so it's just the opposite. And that's also going to give you a stable equilibrium. So that's 2 possibilities right there. And you've already hopefully getting a start on what those axes are going to look like, even if we haven't drawn the lines and arrows on yet. Our third possibility is coexistence. Thinking about what we've discussed so far, what do you think we're going to have to do to get coexistence? Coexistence is essentially neither one of them win, right? And so how can we create a situation where neither one of them can win? Yeah, we just have to flip these 2. That's really all we have to do to get coexistence, right? Neither one of them can reach a population size that completely suppresses the other. That's all we really have to do to get coexistence. Just have to flip these 2 numbers. And make sure I was flipping the right ones, but I was. See, haven't glitched that badly. I flip these 2 numbers, and then N1 can't, well, neither species can reach carrying capacity enough to suppress the other. I did it backwards though, didn't I? Y'all let me do it backwards, and then I said it didn't glitch. We gotta switch these 2 numbers. Yeah. Crap. We was doing so well. We made it so far into it. Y'all gotta catch it faster, and that makes me feel better when you do catch it, because that means you're on board, right? You know what's going on. All right, in this particular case, if we flip the right numbers over here, it's going to, neither species can get an edge, and you actually do get a stable equilibrium. You get a stable equilibrium where they both coexist. And so the last one is the messiest one. It's not that hard to understand once we get the model drawn and up. And that is an unstable equilibrium at coexistence. And to do that one, what's going to happen is you flip this one, and then you end up with a coin toss unless you know something more about the species. In our models, you end up with a coin toss as to which species gets the edge on the other. And so if N1 is able to gather the resources faster than N2, it'll win. If N1 is able to gather resources the fastest, then it'll win. There is a little point in this graph, that's the unstable part, in which they are able to coexist. However, if it shifts just a little bit in any direction, then it becomes unstable. And which species when really depends on the interactions between the two species. That's the one I feel like we need the whole model to really understand completely. Okay. Any questions about any of that? So on Wednesday, we got about 10. We got done with 10 minutes to spare. On Wednesday, there is no PowerPoint. There's no PowerPoint on Canvas. I will be drawing the models on the board and giving you your homework assignment, which will be based on the models I draw on the board. Okay, and so that means I need to do a lot of stretching. And then I need y'all to look over all the stuff that we talked about today.